going to continue doing is we have a little more to work with here in this section 1.4. And then we'll finish up section 1.4. And if there's time today, go ahead and move into chapter 2. All right, with section 1.4, is that large enough for everyone to be able to read? Is that okay? I don't want this semester to be an eye exam for you. We're constantly trying to read the little print. Okay, when we had concluded class the last time, we finished with something that I kind of hinted at. It's called a difference quotient. And hopefully if you have some notes, this is about where your notes ended. Okay, I'll always try to pick up about where we left off so that your notes have some continuity to them. A difference quotient is exactly as the name implies. A difference means something's being subtracted, and it involves some division, a quotient. It's actually a way of looking at slope. Up to this point, we've been doing a lot with slope. And what the difference quotient it really is remember, with slope, you have something like y2 minus y1 over x2 minus x1. Does that look familiar for slope? It requires 2 points. Okay, let's say we have a function, and I'm going to do a little thinking over here in a box. I'll change the color of this so it'll remind us it's some side thinking. Let's say this is x squared plus x. Where did I get that? I just made it up. Let's say it's the function we're going to work with here. Now x squared plus x is going to have what general shape to it? It's a parabola, and it's opening up. You were going like this, which is exactly right. It's opening upward, isn't it? It'll have x-intercepts at, well, let's see, that factors into x times x plus 1, doesn't it? Do you see that? X times x plus 1. So it has roots at 0 and negative 1. Does that make sense to everybody? Okay. So this is going to be a parabola. It's going to open upward. It's going to intersect the x-axis at 0 and at 1. So it's going to do something like that. Does that make sense to everybody? Now, what we could do here is we could look at 2 points on this particular parabola, and using any 2 points that we want to pick, let's say we pick this one here, and let's say we pick another one over here. I picked it over to the left because over to the right it was looking a little bit challenging to get a graph. We can pick those 2 points. One of them, we could call this one our x value. Then we've moved over some amount, and we talked about this a little bit the last time. When you take a step over, what's the letter that's used to indicate that, hey, we've moved over a little bit? H. So this amount that we're going to move over is H. The second point, that red point dot to the right-hand side, is going to be at x plus h, isn't it? Does that make sense? We started wherever x is, and we've moved over however big the step is for h. So we have a second x value here, and this x value is going to be x plus h. Does that make sense to everybody? Okay. When we look at this point here, it has the coordinates x, and how would you get the y value for a particular x value? Let's say it was x equals negative 3. At x equals negative 3, what would the y value equal? Now, I'll give you a hint. There's another way of writing f of x, and that is y, isn't it? Oh, remember how we're used to having functions as y equals something or other? Well, that gives you your y value, doesn't it? So if we say f of x, that's also saying here is the y value. It goes by either name. Okay, I go by a couple names, Dr. Emenacker, Charles, Dad. Okay, variety names, it's all me, regardless which name you holler out. If we want the y value when x is -3, how would you get that? Well, there's a recipe there, isn't it? It says you take the x value, square it, and then you add x to it. So it's -3 squared, +9, plus -3 is 6. So if we were to pick a point, it could be -3 and a y value of 6. Does that make sense? Yeah. I'm just pulling numbers out. Yeah, you're right. I'm just pulling numbers out, trying to make a general example. Now, let's go back to this x value. Something less specific. If I pick the x value as x, to get a y value, I just plug it into the function, don't I? But it's really cool because the x is already plugged in. So to get the y value, I'm just going to put down, I could put y there, or I could put, what's the other name for y? F of x. So I could put f of x. So there's a set of points. So one set of points could be x f of x. Does that make sense? Let's move to that point further to the right. What is the x value? Well, it's going to be exactly x plus h. Then, corresponding to that particular x value, how would you get the y value? Well, like the commercial says, plug it in, plug it in. We would plug it into our function, wouldn't we? And what we would do is, in the function, we would put in x plus h. Does that make sense to everybody? You can either use numbers like the -3, 6. You can use the variable x and get f of x. Or we could use a different variable, x plus h, and you get f at x plus h. Now you're looking at me kind of like, yeah, what's he up to? He's got something up his sleeve. Well, not much. I've got on short sleeves. Okay. What we can do is, do you see these 2 points, x f of x, and x plus h, f of x plus h? We could make a slope out of those. Ooh. Let's think about that for a minute. If we were to do the slope, what it wants us to do is to choose a point that has a y2 and an x2 value first. Do you buy that? For the x2 and the y2, I'm going to choose the stuff further to the right because usually we start on the left and go from left to right. So 2 would be further to the right than 1. Does everybody buy that? What I'm going to do is I'm going to rewrite y2 is f of x plus h over x2, which is x plus h. Does that make sense? All I did was I took this point here and plugged it in to the slope formula. Everybody good? I'm going kind of slowly with this because this is a really important form for down the road and for future classes, depending on where you're headed. Okay? If at some point you find yourself in calculus, half of all calculus is built off of what we're doing right now. Half of it. Now, the other x, or the other point that we can plug in is that one. This would be the y1, which is f of x, over x1, which we're just going to call x. Are you okay? Does it make sense to you that all we've done there is to create a slope? It's a slope between 2 points. What don't you like?
I did it. I was just...
Okay, I saw you shaking your head no, and I thought, I don't want to lose her. Okay, now, if we do the slope between these 2 points, what we're really doing is we're doing the slope of that line there, aren't we? See the little line that popped up here? We're doing the slope from that point x, f of x, to the point x plus h. Everybody good with that? Okay. Then what we're going to do, get these out of the way so we got some room to work. Is this quotient can be cleaned up just a little bit. The numerator can't be cleaned up. There's nothing there that we can really work with. However, in the denominator, can that be simplified? We have x plus h minus x. What's that give you? Just gives you h in the bottom, doesn't it? Does everybody buy that? Okay. The difference quotient is referred to as being either this, or more often it is simplified and referred to as that. Why is this important? Well, what's going to come into play is we're going to want to do slopes on curved lines. Dude, you can't do a slope on a curved line. Slopes belong to lines, don't they? Like y equals mx plus b, that's a linear equation. Okay? Well, what's going to happen here is, down the road, you're going to have a piece of the function that looks like this. I've just taken this one little piece of it right here and enlarged it. We've got one of the points here. We have one of the points there. And what we want to do is we want to know, for example, let's say we want to know the slope here. We can take, and to do a slope, you need 2 points. So what we could do is we could use those 2 points, and that'll be kind of a guess at a slope, won't it? It's not great, but it's not horrible. We can improve our guess at the slope by taking this point and moving it over this way some. And when we move it over that way some, now our slope is like that. At this point, the slope is really the tangent line. However, as we take the other point and we slide it in closer and closer, do you see how it gets closer to being the slope of the tangent line? And as we take that point on the right and slide it closer, what's happening to the size of h? The distance between the 2 points is getting smaller, right? So what happens to the step size that you need to get to the other point? Is the step that I need to take getting bigger? Or is the step that I need to take getting smaller? As we let h get smaller and smaller, these 2 points move closer together. Do you see that? And it allows you to get a good estimate of the slope at 1 point. Now that's kind of weird, the slope at a point. I thought a slope took 2 points, right? It does. But the idea here is we're going to let h get really, 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 really tiny, so there's not much distance between those 2 points. And it gets almost to looking like we're doing the slope at 1 point, but the 2 points are just a teeny little bit apart. So you've got 2 points, and you can do the slope. That's how you wind up estimating slopes on a curve. Well, that's all well and good and cute and all this other stuff, Chuck, but why would I ever want a slope on a curve? Okay? You're looking at sales of a product. And what's happened is you have hired a new firm to market your product. The product was in a down say you don't even have this. You don't have that. You hired in the new company, okay? And the new company, let's say, came in right about here. And a month later, you're looking at sales, and you're saying, you know, they're still going down. This is not looking good. Should we fire that company? Should you or shouldn't you? Well, what you need to look at is the trend since they've been hired. If you look over here, the slope was pretty big negative, wasn't it? And let's say we really hired them over here. This was the hire date. And this is where we are today. Things are still going down. But what has happened to how fast they're going down? Do you see it's kind of leveling off? If you do not look at the slopes, okay, the one slope is really steep here. The company now, through their efforts, has a slope like that. Are things changing in the direction you want to see them changing? Is the company going downhill as fast as it was? Or is it slowing? It's slowing, isn't it? And what the company who you hired is going to try and make a case for is, you know what? We're turning things around. And if you give us a little more time, we are projecting that with a little more time, the slope's going to start going like this. Is that good news with that slope? What's that tell you is happening to sales? They're turning around and they're starting to go back up. A very important thing that can be seen from slopes is how are trends changing. You've got to know how trends are changing in business to stay alive. If Ford had never noticed that the trend was moving away from the Model A, Ford would still be building what? The Model A Ford. They're cute, but how many of you would really want to drive one every day? None of you? You mean you don't want the open windows and stuff? And the windshield wipers you got to work by hand? Okay. If they would have never noticed things were changing, they'd still be back there. Same thing is true with whatever company you're going to own or work with. And the ability to track what's going on comes from looking at slopes, which comes from this difference quotient. The ability to see what's happening at any point in time is this difference quotient where you let h get really small. You pick 2 points that are really close to each other, and you get as good of an estimate as you can of what the slope is at that point in time. How are things changing right then and there? Because you've got to decide right here and now, do we sign another 2-month contract with this company or not? What would you say based on the data that you got there? Give them another 2 months or go shopping? It's your call. What you gonna do? Have some guts. The worst you can do is be wrong. And in here, it's not the end of the world. Please? Go sign? You'd go shopping? Okay, what would you be looking for? Maybe somebody could get the growing more quickly. Okay, there's that possibility. So some people are going to say, you know what, go shopping. I wanted things to turn around faster. I really thought they could get things turned around faster. And you know what, that's perfectly legit to say go shopping because I was expecting things to turn around faster. You know what some people are going to say? I'm going to stick with them because, you know what, we were in this death spiral here, and at least they've got us to here and projecting there. It looks like things are getting turned around. The question is one of whether you are satisfied with the time frame in which it's getting turned around. Whoa, Chuck, wait a minute. You just said both answers were okay. This is a math class. There's only one answer, right? No. What I'm trying to do is get things more realistic in the real world. There's more than one answer. That's what makes it awful on Friday nights if I come home and say, want to go out and eat? Well, everybody says yes, and then you know what the next question is, right? Where? This is where the problem comes in. Why? There's more than one answer, isn't there? There's more than one opportunity. Based on how you interpret things here, there's more than one answer, more than one opportunity. In the real world, that is routinely the case. I want to get you used to the idea that, you know what? More than one answer depending on how you interpret things. Okay? And you can say, you know, I really wanted them to turn around faster. I think I'll go shopping. And hey, if nothing else, we can hire them. Okay? All right. So we've got this difference quotient. Is everybody okay with that? You're going to hear this again about there's more than one answer, I promise. It's going to keep bumping up against our problems all the way up through May. Let's take a look at something like this. Let's say that we have something like f of x. Now, I'm just giving you an equation. The equation would typically describe some kind of sales, the rate at which some medication is absorbed, or the rate at which some population's growing, or something or other. It's normally going to describe some real live thing. Right now we're using a very simple, uninvolved equation that we can practice on. Make sense? Okay. So if you're thinking, well, I don't see where this fits in with anything in the real world, this is just practice. Okay, so we've got that. Let's compute the difference quotient. This is not intended to be a subliminal message you go to DQ for ice cream or something. It's difference quotient. Remember, the difference quotient basically says we're going to take f at x plus h minus f at x and divide by what? H. Now, what we need to do is to understand what the symbol means. That's one of the tricky parts in math, is what do all these squiggle marks really telling us to do? Well, part of it's easy. Good, let's do the easy part. It's called partial credit. Put an H in the bottom. I can do that. For the first little piece, okay, we're just looking at the first little piece. That's this, the first term in the numerator. It says find your equation named f. Can you find it? Yeah, it's up in the upper left corner, isn't it? Then, once you find it, what are we going to plug into each of the slots in that equation? X plus h, does that make sense? Well, it says to first copy down the equation, and every place there is a variable, leave a place to plug something in. And what we're going to plug in, is this. So we're going to go over to here, we're going to pick up the x plus h and plug it in each location. Everybody okay so far? Now I'm going to walk away from that for a minute. Minus. This second part here says find the function named f. Okay, well that's 2 times something or other minus something or other squared. For this second part of the formula though, in this case we're just going to plug in x, which is going to give us, oh wow, that's going to give us back our original function, isn't it? 2x minus x squared. Does that make sense? Okay, time for some algebra. Wait a minute. That's what we're here for. On this first term, thank you. What are we going to do when we have 2 times the sum of x plus h? It's okay to distribute there? Okay. So that's going to give us 2x plus 2h minus, now remember the please excuse my dear Aunt Sally stuff? You do the stuff inside the parentheses first, that's please. What's excuse? Exponents. What's the exponent applied to that? 2. So we need to square that, don't we? And be careful. Be really careful. X plus h squared is not x squared plus h squared. It's not that. You don't just take the exponent and distribute it. But what you really do, this really means to take x plus h times x plus h. Oh man, you got to FOIL that out, don't you? Does that look familiar to everybody? And when you do that, you're going to get x squared 2xh plus h squared. Now, is there anybody who's confused with that? Is there anybody who's confused but won't raise their hand or let me know? Right. So what I did is I took x times x squared, x times h, which was xh, then do the inner 2, which is x times h, then do the last 2, which is h squared, and you're absolutely right. Now we can combine some like terms, and that'll give us 2xh and the h squared. Now, there's something wrong in the numerator. I did it on purpose because I want to draw your attention to it. It's a very subtle thing. We're subtracting the x plus h squared stuff, aren't we? I said subtract there, didn't I? But does it subtract the entire deal or just part of it? Well, right now it's only subtracting the x squared. You've got to put parentheses around there. Oh, does that make sense? Because it's the whole thing being subtracted. So be careful of that. Now, we still have our minus. We're going to have 2x minus x squared. Everybody okay? Equals. We have 2x plus 2h. Then what I'm going to do is take this subtraction and distribute it, the negative, and distribute it. Minus x squared minus 2xh minus h squared. Everybody good? Then we're going to take this subtraction here and distribute it. It's going to be minus 2x plus x squared over h. Are you feeling like this is getting to be a big mess? It's going to hopefully start to simplify some at this point. Let's see if there's some things that we can combine. Well, what we really have is this 2x plus 2h minus x squared minus 2xh minus h squared minus 2x plus x squared all over h. There. Following me so far? What'll cancel? Yeah. Do you see this 2x here? It'll cancel with that minus 2x there, won't it? Anything else that'll subtract off or cancel out? Good. We have a minus x squared plus x squared. That cancels out. Well, that means we can simplify this a little bit. Let's write down what we have left. We have a 2h minus 2xh minus h squared all over h. Are you with me so far? I don't want to lose you anywhere. I know I'm going to keep asking, and I'll do this all semester. Does this make sense? Do you follow me? Are you here? Because I don't want you lost. In the numerator, everything has a factor of h with it, doesn't it? So we could factor out the h. You see it, it's 2h, 2xh, h squared. So we could factor out an h, and when we do, we'll be left with 2 minus 2x minus h. Are you okay? Yeah. Well, what I've done is I've factored an h out. And what the brackets say is everything inside here is really times an h. This h that was factored out from up there. Because if we distribute it, we're going to get 2h. Oh, yeah, here it is. We're going to get 2xh. And we're going to get h squared, just like we had in the line above. Well, gosh, Chuck, why'd you go and factor it out? Just trying to make this stuff worse for us? Well, believe it or not, there's something here that'll cancel. Do you see it? Those h's will cancel now? And once they cancel, we can rewrite this as 2 minus 2x minus h. Yeah, it looks a little better. And you may be thinking, well, whoop-de-doo, what's the use of that? For right now, what we're trying to do is get you used to the algebra. That was probably a little more algebra than you're used to, isn't it? Yeah, that was a whole new world, huh? Whole new can of worms, whole new something or other. What this does is it allows you to figure out what the slope is at a particular point. Now remember, we talked earlier about this h value. And the h value is what allows the second point to be sitting out here, isn't it? Well, if we look at this formula that you just cooked up down at the bottom of the screen, if we're trying to estimate the slope over at this point here, what's happening to h? You're sliding this other point in, and the h value is getting bigger or littler? Littler. It's getting smaller and smaller. And it's going to get to the point that h is 0.00000000001. Is that very much? Which in the end is going to allow us to say, you know, okay, h is still there, but it's so small we're going to ignore it. Is there a piece of dust somewhere on your right sleeve somewhere? I don't know, Chuck. I didn't really bother looking. But yeah, I guess there's a piece there somewhere. But you know, it's so small, I'm not even going to worry about it. Were you worried about that piece of dust on your right sleeve? Didn't even think about it, you just mentioned it. That's how important it was. Okay? What this does then is it gives us a formula for the slope at a point. It gives us an equation where we're going to wind up with the slope is equal to 2 minus 2x. Now the cool thing is with this, if we graph this equation, where'd it go? 2x minus x squared. Remember we have y equals 2x minus x squared. Well, let's say that's going to be x times 2 minus x. So that's going to give us something that goes through at 0 and 2. Now, does this parabola open up or down? Down. Got it. Does this make sense how I factored it? Just pulled an x out. That gives you two roots. One is x equals 0. The other is x equals 2. This thing's going to do something like this. Okay, so let's check. Does this really look like it could be giving us the slopes at different locations? What's the slope at x equals 0? Well, according to this, it's going to be 2 minus 2 times, what's the x value? 0. The slope is 2. If we drew a tangent line there, does that look like it could be a slope of 2? Well, at least it's going up, and it's pretty steep, isn't it? How about if we look at the slope when x is 1? That's going to be 2 minus 2 times whatever the x value is. Now, what's the x value this time? 1. What's that going to be? 0. If x is 1, we're right about there. What's the slope of the tangent line there? Do you see that it's 0? Wow. Interesting. Suppose we do the slope at x equals 2. 2 minus 2 times whatever the x value is going to work out to be negative 2. Do you buy that? So if we go over to x equals 2, slope something like that. Is the slope going down? Look at this point way over here. Is this a downhill slope? Yeah, so that means the slope's going to be a negative value, isn't it? Does that match? Does that match what we estimated the slope to be there? The cool thing about this, see in the middle up there where it says m equals 2 minus 2x, regardless what x value you pick, plug it in there and it'll tell you what the slope is at that point. It'll tell you how fast things are changing and whether they're increasing or decreasing. So this difference quotient that you just worked through is important because it allows you to understand how a function is behaving anywhere on the graph. A very important thing that this function does is it allows you to see where the graph is 0. Oh gosh, Chuck, that's kind of silly. Why would I care about where the graph equals, or where the slope is 0? Sorry. It allows you to see where the slope is 0. If you have a function that goes like this, you have a 0 here for slope, a 0 here for slope, a 0 here for slope. If you're looking for the best profit possible, the top profit, let's say here x equals 2, 4, and 7. Which x value is going to give you the highest profit? 7. It's going to occur where the slope is 0, isn't it? Because that's where the graph turns. But if you know where the graph is 0, you know exactly where to look. Here, here, here. There are 3 possibilities. Well, gosh, Chuck, that's kind of stupid. Sorry, my wife told me never to say that word. It's not a nice word in her vocabulary. Chuck, that's illogical. I can look at the graph. Okay, let's take a quick trip to Kroger's. How many different products does Kroger's have on the shelves? A whole bunch of them. Each product has its own variable assigned to it, like X, Y, Z. Oops, there are only 26 letters in the alphabet. Kroger's has more than 26 products, don't they? So they call them X of 1, X of 2, X of 3, X of 500, X of 637. Now they can account for every single product. If you tried to graph that with, let's say, 2,500 variables, if you tried to do a graph with 2,500 variables, could you do that? The graph up there has one variable, x, and a y value. If you have one variable, it requires 2 dimensions to graph it. If you have 2,500 variables, how many dimensions does that take? 2,501. Well, you just add one more to it. Okay, the one more being for the y-axis, the profit. You would need a graph in 2,501 dimensions. Let's back that off a little bit. This room is how many dimensions? 3. If we throw the clock in, we're living in 4. Have you ever gone beyond 4 dimensions? Length, width, height, and time? No, Chuck, I'd never even thought about it till you just brought it up. The problem in the business world is trying to find profits and costs in hundreds and thousands of dimension problems. You can't graph it. You can't. Not just because you haven't had some other math class. Doesn't matter how many math classes you've taken, you can't graph it. But you still have to find out where's the best profit, even though you can't draw a picture of it, ever. And you still have to know it's the best choice, even though you're never going to see a picture of it, ever. That's where you're using stuff with slopes. This stuff is killer important. It may not be that you ever wind up in some sort of a management position in business, but if you ever do, is maximizing your profit something that you'll want to try and do? This is how you do it. Is minimizing your costs something that would be nice to do? Once again, because are you going to have more than two things that affect the cost in your business? Just the electric and the water bill, two things that affect the cost, and now you're done. You can't graph anymore. You haven't even gotten to your employees working, retirement, insurance, or even buying the product to put on the shelves. So you're already out of dimensions. Does this make sense on why this is handy? It allows you to find where things are zero, even though you can never in the physical world see it. Every single business runs off of this. Okay. Does it make sense how to do these difference quotients? I know we just did one, but I thought if I did one more slowly than doing three of them really fast, it might sink in a little bit more. One of the nice things about having a movie is when you get home and it's Sunday night and you say, oh crud, what did we do in there? We did Dairy Queen. No, it wasn't Dairy Queen. It was something else, DQ. Oh yeah, it was those difference quotients. You can always go back to the movie to see a replay. And then when you say, whoa, that hurt my brain, back it up on the timeline and play it again. And it won't hurt so much the next time. And it'll get to the point where it actually starts to make sense. Does that make sense to everybody? Okay. Now, I spent a little time as well explaining why these difference quotients are important. Okay? Quiet already. It's getting embarrassing. It's very, very important. It's a very, very important idea. If you're going anywhere mathematically beyond this class, it's a very important idea. Half of everything that all of calculus does depends on what's up there in the upper left corner. Half of the course is off of that. Let's see here. We've got till 20 after, right? Which gives us about 10 minutes. Let's take a run at a couple of things in section 2.1. It's okay. I haven't forgotten the quiz. It's right here. Okay, I haven't forgotten it. Don't worry about it for the next 10 minutes. Let's jump into section 2.1. Oops. Okay, we're going to talk about equations of lines. Back on the home turf. These difference quotients are kind of scary. It's all about slopes, and slopes are part of what goes into the equation of a line, isn't it? Okay? Basically, three general ways that this equation of a line can come. Any idea what one form or one name for an equation of a line is? Digging deep. Digging deep. I'll give you a hint. Maybe this will get you started. Does that sound familiar? Point slope form? Ah, yeah. Okay, I've mentioned before, in mathematics, they're really clever about how they name things. They either name it after the person who thought of it, or they name it after what it's really doing. What does this equation have in it? Take a real wild guess. Part of what it has in it is a point, and the other thing it has in it is a slope. Whoa. Okay? The way the equation looks is y minus y1 equals m times x minus x1. And I have people come up to me on quizzes and tests. Chuck, I forget if it's the point slope or the slope-intercept that has the intercept in it. I'll say, well, think about it. Well, I have. I'm not sure which it is. Okay? You're not going to miss that one, right? What's the x1 and the y1 in that particular equation representing? A particular point on the line. So for example, let's say we have a line and let's say the line goes like this. I'm just making up a line in case you're thinking, where did he get this anyway? It just popped out of my head. And this line, let's say, has the point 1, 1 on it. And let's say the line has a slope of 3. Now you want to use the equation of that line to try and project what the value is going to be at x equals 4, what x is going to, or what it's going to be when x is 7. You want to know what's going to happen in the future. Does anybody ever do that? Yeah, it's called weather forecasting, right? It's called the forecast for next quarter's sales. Do you think all the big stores have already got their forecasts in on Christmas sales? Yeah, because when did they have to order the toys and everything else they're planning on selling at Christmas? Do you think they ordered that after Thanksgiving? That's already done. That's ordered. That ship has sailed. They've got a forecast way in the future on this stuff. Okay? So let's see what we can do with this. What we're going to have here is y minus, what's the y value? 1 equals the slope, which is 3, times x minus, the x value is also 1. This is going to, we can clean this up some when we distribute the 3, like that. Everybody okay? And we can clean this up a little bit more by adding 1 to each side. And now we have that equation. The advantage to this new form of the equation is if x is 4, what's the y value going to be? Oh, I messed up. That can't have a slope of 3. What's it have to have? -3. Thank you. I can't believe I did that. I was getting concerned about time and I messed up. We have a slope of -3, so this is going to be a -3 plus 3x. This is going to be a -3. And now what's that constant going to be? Does that make sense what I changed it? Okay. We're going to have +4, aren't we? Now, if x equals 5, what's the y value going to be? -11. That's it. All you got to do is plug 5 in for x, right? -3 times 5 is -15, plus 4 is -11. This allows us to make some prediction of where we're going to be as x gets bigger and bigger and bigger, or as x gets smaller and smaller and smaller. Okay? Yeah, where the 4 came from is I want to get y by itself. So what I'm going to do is I'm going to add 1 here to get that to cancel out. And oh yeah, what I do to one side, have to do to the other side. Sneaky, huh? Okay. This other form of the equation, anybody recognize what that is? Y equals a -3x plus 4. Is that a particular type or form for an equation? Slope-intercept, way to go. Bless you. Slope-intercept form is y, and you're all going to recognize this, mx plus b. M's the slope, what's b? The y-intercept. Now, if we look at that equation that we have up here, it's kind of fun getting to choose all these colors. If we look at this equation up here, we can see the slope is -3, right? What is the y-intercept? 4. It goes through the y-axis at 4 when the x value is what? 0. Remember, if you're on the y-axis, the y-intercept, talking about the y-intercept, that's when the x value is 0. So here's a second form of an equation. What if you're given something like this? You're given 2 points. Let's say -2, 5, and say 3, 7. And you're asked to compute the equation of the line in slope-intercept form. How would you do that? Other than look at the clock and say, rats, we got 3 minutes left. That's probably enough time for him to get it done. It is, yeah. Yeah, and that'll compute the slope for us. That's an important part of this. What we're going to do first.
Isn't it y2 though first?
I'm sorry?
Isn't it y2 minus y1?
Yeah, it's y2 minus y1, or you could do y1 minus y2 over x1 minus x2, as long as the x and the y values are from the same point. But traditionally, it's y2 minus y1 over x2 minus x1. But whoa, he's getting a little flexible on us here. Yeah, okay? Okay, the main thing to remember is when you pick a point, you do its y value over its x value minus, go to the other point, do its y value over its x value. That's the key thing. If you remember that, it'll work all the time. This is going to give us 2 over what? 5. Now, we want to come up with an equation in slope-intercept form because that's easier to work with in the long run. That means we want to get y equals mx plus b. But we don't know what the slope-intercept is. There are 2 ways to get it. One, we could go back up to the point-slope form, like we just did, couldn't we? Plug it in, and then we end up with a slope-intercept form? You buy that? So one way to do this then would be to do something like y minus 7 equals 2/5 x minus 3, and then simplify. Does that make sense to everybody? That's one way to do it. However, there's another way to do this. We could write down the equation we want. We want y equals mx plus b. Don't we? Do we know what m equals? Yeah, it's 2/5, isn't it? Now, it says you take a y value and you take an x value. Do we have a y value and an x value that we know for sure is on this line? Yeah, in fact, we know 2 of them, don't we? Which one of those points should we select? -2,5 or 3,7? 3,7. Would you have been wrong to have said -2,5? No, just probably avoiding the negatives. Okay, so I'm going to put the 7 over on the left side, the 3 over on the right side, and plus b. Everybody good? Okay. So this is going to give us 7 equals 6 over 5 plus b. Oh, we need a common denominator of 5, so this is going to be 35 over 5. Then I can subtract the 6 over 5, equals B. Now I did a couple of things there. Are you okay with that? I got a common denominator and moved the constant over to the left side. So it's going to give us 29 over 5 equals B. Well, wait a minute. We can write our equation now. Y equals 2/5 x plus B. What's B? 29/5. And there's your equation. There are two different ways to go about getting the equation in slope-intercept form. Which is the right way to do it? Both. Whichever one you're more comfortable with. And sometimes I'll choose one over the other depending on the numbers. Are you okay? Hey, you see these? Imagine me being sick and say, what's your name? Kevin. Kevin, I feel awful. Would you go to the doctor and get a checkup for me? Kevin looks at me and says, whatever. And he comes back, doctor says I feel great, or I look great, there's nothing wrong with me. Gosh, I don't understand why I'm sick. That'd be stupid, wouldn't it? That's not going to give any feedback on me. On these quizzes, can I follow you around all weekend and make sure that you don't get any help? No. But if you go get help from others, are you going to know what you know and don't know when it comes test time? No. Take this just like you were here in class, so do Monday at the beginning of class. Okay, hard copy here Monday at the beginning of class. If you can't be here, give it to somebody else in the class, or stick it under my office before class meets. There you go. Grab yourself a copy. I hope you have a terrific weekend.